Hello everyone. Today our course will take you through hydrodynamic lubrication. Imagine two massive pieces of metal weighing several tons, rubbing against each other at 5,000 revolutions per minute. In any normal world, they would weld together or grind into dust within seconds. But they don't. Why? Most people say, because of oil. But oil isn't just slippery. In high-speed machinery, the oil actually lifts the metal and holds it in the air. This is hydrodynamic lubrication. Today we're going to look at the fluid wedge, how pressure is born out of thin air, well, thin oil, and how machines stay alive. What is hydrodynamic lubrication? In mechanical engineering, we categorize lubrication into three main types: boundary, mixed, and hydrodynamic. Boundary. Metal touches metal. Mixed. A bit of both. Hydrodynamic. This is the holy grail. In the hydrodynamic regime, the moving surfaces are completely separated by a thin film of liquid. There is zero metal-to-metal contact. It's like a car hydroplaning on a wet road. The tires lose contact with the asphalt because the water can't move out of the way fast enough. In a bearing, we do this on purpose. The secret ingredient: the fluid wedge. How does a liquid, which you can pour out of a bottle, suddenly become strong enough to support a 50-ton rotor? It all comes down to the converging wedge. Imagine a flat slider moving over a surface covered in oil. If the surfaces are perfectly parallel, the oil just flows through. But if we tilt that slider just a little bit, creating a wide entrance and a narrow exit, something magical happens. As the oil is dragged into that narrowing gap by the moving part, it gets squeezed. Because liquids are incompressible, that squeeze creates a massive spike in internal pressure. This pressure pushes back against the load, keeping the surfaces apart. The journal bearing, a real-world example. Let's look at the most common application: the journal bearing, or sleeve bearing. You'll find these in every internal combustion engine and large generator. At rest. The shaft, journal, sits at the bottom of the bearing. Metal touches metal. Startup. The shaft begins to rotate. It climbs up the side of the bearing wall slightly due to friction. Full speed. As the speed increases, it pumps oil into the space underneath itself. This creates a high-pressure oil wedge that shifts the shaft to an eccentric position. Interestingly, the shaft doesn't sit right in the middle. It sits slightly off-center to maintain that wedge. The Reynolds Equation. We can't talk about this without mentioning Osborne Reynolds. He gave us the math that proves this works. Without getting too deep into the weeds, the pressure generated depends on three main things: viscosity, how thick is the oil; velocity, how fast is the surface moving; geometry, how tight is the gap. If the oil is too thin, the wedge collapses. If the speed is too slow, the wedge never forms. This is why most engine wear happens during cold starts. The speed is low, and the oil hasn't reached the right spots yet. Why does it fail? If hydrodynamic lubrication is so perfect, why do machines break? Contamination. A tiny piece of dirt is harder than the oil film. It will bridge the gap and scratch the metal. Overheating. As oil gets hot, it loses viscosity, becomes watery. If it gets too thin, the wedge pops, and you get metal-on-metal contact. Low speed, high load. If you put too much weight on a shaft moving too slowly, the pressure won't be enough to lift it. So, to summarize, hydrodynamic lubrication is the science of using motion and geometry to turn a simple liquid into a high-pressure cushion. It's what allows our modern world to spin. If you found this helpful, hit the like button. It really helps the channel grow. I'm also planning a deep dive into hydrostatic lubrication next, where we use pumps to create the pressure. Thanks for watching Gyan. Keep learning, keep engineering. I'll see you in the next one.